Swayam Prabha. Digital India. Educated India. Swayam Prabha. Digital India. Educated India.
Good day, everyone. It's a pleasure to meet you once more. Today, we are going to delve into the part 2 of my lecture on the subject or the topic of air navigation. Let's have a brief recap of what we carried out in part 1 of this lecture. The previous lecture started with providing details or brief details about what are the basics of air navigation, what are the different objectives and factors that are associated with any air navigation process, and then we ventured on to the different flight rules that are implemented to carry out the air navigation, that is visual flight rules and the instrument flight rules. The visual flight rules, through the presentation we also try to understand what are the two different methods carried out to carry out visual navigation, that is pilotage and dead reckoning. These methods basically made use of a specific geometrical tool called the wind triangle to carry out the required calculations, which were helpful to understand what is the underlying drift and wind correction angle that the pilot needs to adjust his or her aircraft to, so that the true course that has been planned for can be carried. Subsequently, we also tried to look into the basics of the different instruments that are used to carry out VFR navigation, that is the compass and heading indicator. Subsequently, in the latter part of the particular presentation, we also dwelled into the other aspect of of air navigation, that is based on instrument flight rules, and also we try to understand what are the different 6-pack instruments that are implemented to carry out such an IFR based navigation. So as we can understand from the previous presentation, we were able to understand what are the various basic instruments that are integrated onto the aircraft to carry out air navigation. All these navigation tools were effective when a communication with respect to the ground station was not required. However, there are instances, or there may be some instances, wherein proper visual references are not available, and the overall air navigation has to make use of radio navigation. So in this part 2 of the lecture on air navigation, we will cover relevant topic related to a key part of air navigation, that is electronic or radio navigation. This type of navigation basically makes use of a number of onboard instruments, radio navigation aids to carry out the navigation. So what it does is the aircraft needs to tune into a particular radio navigation aid, and based on the underlying phenomena, underlying principle, the nav aid will be able to provide proper assistance to the aircraft to carry out the overall navigation towards the navigation aid to which the aircraft has been tuned into. Through this lecture, we will be covering certain navigation aids like the force course radio range, the marker beacons. Then we will be understanding what are the different what are other navigation units that are used by aircrafts, that is the non-directional beacons, or more commonly known as NDBs. Then we will look into the compass locator, the visual aural range radio navigation aid, and one of the most famous and the most prominently used navigation aid, that is the VOR or VHF, omnidirectional range. Subsequently, the presentation will be concluded by providing brief details related to the distance measuring equipment and the instrument landing system, which are a key part of carrying out navigation during the landing phase of any flight. So, with the evolution of radio navigation systems, the first and the foremost type of radio navigation equipment that was implemented on aircrafts was called the force course radio range. Now, these navigation aids consist of 4 radio towers that are placed in a square pattern. These these antennas basically transmit their respective signals outward, and based on a particular phenomena of overlapping, the aircraft can carry out the navigation towards the particular radio station. Now, these were installed in the early 1920s. As I mentioned to you, it was during the preliminary phase of implementing radio navigation to carry out aviation. These were subsequently used up till 1950s on a very wide scale. In fact, these were found to be so crucial to carry out air navigation that a number spanning more than 400 of such ground stations were installed all across USA and Canada. A sequence of 2 of these 4-course radio range ground stations acted as a airway route between 2 waypoints, and hence these proved to be very vital to carry out navigation when the overall outside visibility was low, and hence the aviators could navigate their plane in a very efficient manner. So, the most notable feature related to this is that these operate in a low frequency range spectrum. So, when I am talking about the low frequency range spectrum, we need to understand whenever the frequency is as such a low frequency value, they are prone to distortions associated with outside environment, and hence their range gets compromised because of these interferences. So, this is a point the viewers should take note of, which will be helpful for the subsequent slides. Now, how this radio range operates is in the following way. So, as I mentioned to you earlier, there are 4 towers that are placed adjacent to each other in a square pattern. These towers emit their own respective signal, and there is an underlying overlapping region between the two, which is pointed out in the red region. In fact, this overlapping region determines the on course leg towards the navigation aid. So, suppose a plane is entering from an A quadrant, the pilot would hear a signal in the form of a series of bip and beep, that is described as dot and dash. Then if a pilot hears such type of a tone, he will understand that he is in the A quadrant of the particular radio navigation radio range. Suppose the pilot hears a beep, beep, bip sound tone, he will understand that he is entering from the end sector of the radio range. And if the pilot hears a steady tone, which corresponds to the overlapping region between two adjacent lobes, then the pilot will understand that he or she is on the on course leg towards the navigation aid. So there are certain drawbacks that are associated with such type of navigation aids, most notably because the pilot will never be able to actually determine what is the on course leg, and course correction heading was difficult to obtain, and thus whenever a pilot would understand that he is in a particular sector, that is A or N, he would have to carry out a series of hit and trial processes to intersect with the on course leg, and hence it was a very difficult task for pilots to carry out navigation using this navigation aid. Moreover, there is no distance estimation possible through this navigation aid, and as I already mentioned to you, because they operate in a low frequency range, they are highly amenable to distortions and reflections from lightning, and hence the overall accuracy, which was already very limited and constrained, gets severely hampered, and hence the overall accuracy of the navigation provided is compromised. So then as the time progressed, there were introduction of certain other navigation tools with this particular system. The first of them is called the introduction of marker beacons. Now these marker beacons are installed on the on course legs of four course radio stations. So how these operated was that a distinctive tone and code would be used to identify the beacon and hence the location of the aircraft with respect to the navigation aid. However, these came with a shortcoming that the usage of these navigation aids and along with the marker beacons was useless if the pilot operated away from any on course legs. So basically these marker beacons were only helpful when the plane was on the actual approach leg of the VR station. Even a slight deviation from the course leg and such type of marker beacons would be unhelpful for carrying out any sort of approach navigation. So as I mentioned to you, because of the high amenability to distortions, they were limited to very short range. And their accuracy was severely hampered. So the efforts were carried out across the world to devise and implement new techniques of radio navigation. One of them was called the non-directional beacon, or more famously known as NDBs. These NDBs were installed in United States in the 1924 and were subsequently used in many places. In fact, many countries are still making use of this rudimentary method of radio navigation to carry out their navigation. This is a small description of how a radio navigation aid would appear on a sectional chart that I mentioned to you in the previous lecture. So when carrying out the aeronautical while carrying out the flight planning, these radio navigation aids also can be taken as waypoints to carry out to implement your flight plan. So how these actually work? The NDBs basically transmit a uniform signal which is called the omnidirectional signal from transmitter using the low and medium frequency band. Let's see how. This is a brief symbolic representation of any NDB signal, and this is how it is represented on a sectional chart. So for example, in this particular figure, this marathon basically explains the fact that this navigation aid is named the marathon, and which operates on a frequency of 260 kilohertz, and hence while carrying carrying out the navigation in flight, the pilot needs to tune in his receiver to this particular frequency to carry out the navigation. So, there are two parts related to a particular NDB navigation. First, the onboard part, that is the that is called the direction finder, and this direction finder basically makes use of a loop type antenna. Initially, during the advent or during the inception of this technology, the loop antenna was manually operated by the pilot from the flight to carry out to receive the signal to carry out navigation. So, how there are two modes associated with non-directional beacons. One, in the first mode, that is A, the navigation signal is perpendicular to the plane of the loop antenna. Because of this relative orientation, the signal received by the loop antenna would be minimum and hence would be indicative of a null position. In the second type of signal reception, the loop antenna would be aligned parallel to the incoming signal, and because of this orientation, the signal reception would be maximum, and based on the orientation of this particular position of the loop antenna, the pilot would be able to hear the transmitted signal and hence would be able to understand the relative bearing of the incoming signal. Now, let us see how how the operation or the usage of this equipment occurs in flight. So, to carry out navigation using the NDB equipment, we need to make use of an additional equipment that is on board with us, that is the magnetic compass. So, using these two methods, that is two instruments, that is magnetic compass and the direction finder instrument, we can calculate the relative bearing that the aircraft is flying with respect to the navigation aid, that is the NDB station. Let us understand this with an example. In this, let us assume that NDB is located at this particular location and the aircraft is at a particular location as described in this figure. Now, when this type of a scenario occurs, the magnetic compass will firstly show heading that is prevailing with respect to the aircraft, that is 30°, and the direction finder would show an indication towards the incoming signal of the navigation aid, that is, in this case it is at around 310. The ADF, the relative bearing to the NDB will be calculated by the addition of both these readings, that is corresponding to the magnetic compass and the direction finder. In this case, the two sum out to be 340°. So, if a pilot wishes to fly towards the NDB, they will have to turn their plane in a manner so that this direction finder antenna arrow is pointed in the forward direction. There is one more usage related to non-directional beacon, that is called the homing. In order to understand this process, suppose there is a wind, suppose there is a true course that has been planned by the pilot between his current location and the predetermined NDB location. Through weather forecast, the pilot after a particular interval of time, the pilot realizes that the plane has drifted away from its actual planned course, and also through the wind data that he has at his disposal, he knows what is the underlying wind condition. So, based on because of the presence of this wind condition, the plane will drift towards a particular direction. In this case, it is towards the right, and the NDB signal, NDB direction finder would basically show that the aircraft has a relative bearing in the left direction, and hence the pilot will have to subsequently adjust his or her heading so that the needle can be put in a straight direction. This process is called the homing and is a very critical part of carrying out navigation in a long duration flight. So one more usage of such type of methods, that is homing, is that if we are able to carry out homing towards two different NDB stations, we can actually establish what is the exact location of our particular aircraft. So as I mentioned to you earlier, the NDB equipments, that is the direction finder instruments, had to be manually operated, and the frequency needed to be adjusted accordingly. Now with the advancement of time, a new advanced version of direction finder has been implemented across the aircrafts, which is called the automatic direction finder antenna. So what these equipments basically electronically determine the bearing of the NDB and displays this information to the pilot, and hence the cumbersome part related to tuning to a particular frequency and subsequently adjusting the direction finder to home towards a particular radio station is reduced, and hence workload related to the pilot is significantly reduced. Apart from making use of the NDB equipments for carrying out homing, there are other utilization of NDB stations, one of them being called the compass locators. Now these compass locators are basically low and medium frequency range operated NDBs that are co-located along with the marker beacons that are placed in the approach leg of ILS systems. So these NDBs help in carrying out interception of the aircraft with respect to the approach leg of the runway. Another usage, an advanced version of 4-course radio range is called the visual aural range. In this method, rather than making use of four aural range stations, the navigation aid makes use of 2 aural and 2 visual range systems, and because of the intersection of these particular 4 different signals, navigation or homing towards the particular navigation aid can be carried out easily. These operated in a VHF spectrum of frequency, and as I mentioned to you earlier, apart from making use of the aural signals that were mentioned to you earlier in the 4-course radio range setup, these systems make use of 2 additional visual signals, that is corresponding to the blue and yellow signals, and hence the sector is divided into 4 parts, 2 sectors corresponding to yellow sector and 2 corresponding to blue sectors, whereas the other 2 corresponding to A and N sectors. So now after with advancement of further radio navigation equipments, another tool was used to carry out navigation, which is called the very high frequency omnidirectional lane, or more famously called as VOR. Now these VORs are basically short range radio navigation systems which uses radio signals transmitted by a network of fixed ground VOR beacons. So as you see in this particular figure, there are such type of radio stations are installed across the predetermined routes, and the pilot can tune into these VOR stations and hence carry out the particular radio navigation. These operate in the VHF band of frequency, that is between 108 to 117.95 megahertz, and hence they have a higher range of around 200 miles. Because of the frequency of these signals, they are highly immune to reflections and static interference. Hence the accuracy of these signals are better compared to the NDB signals. These have, because of the increased accuracy of these navigation aids, these have been used comprehensively since the 1950s to carry out the air navigation. Now the NDB signals basically made use of an omnidirectional signal, that is the signals of equal magnitude in all the direction. These signals were intercepted by the aircraft, and based on the direction of the incoming signal, the plane was able to determine, the pilot was able to determine from which direction the signal is coming. Now, as far as the VR mechanism is concerned, the underlying science is a little different. Let's understand this. So unlike NDBs, VORs transmit an infinite number of navigation courses called radials. Now these radials are selectable by the pilot. So for instance, a pilot has determined a particular VOR station, and he wants to follow or reach that VOR station on a particular course, for example 90-degree. Through the onboard equipment available with the pilot, when he is trying to home towards a VOR station, he or she can actually select the radial that he wants to follow based on the predetermined true course that he has planned. So these towers make use of two types of different signals. One is called the reference phase signal, and the other is called the variable phase signal. Both these signals operate on the same frequency, that is 30 Hz, and are emitted out at the same time. Now let's understand what these two signals that I mentioned to you, that is reference phase and variable phase signals, consist of. The reference phase signal is a signal that is constant in all directions and is constant in the outward and is emitted in an outward direction, whereas a variable phase signal varies with azimuth, and hence each and every radial direction is coded with a particular phase difference, and which the overall term related to this type of modulation is called the phase modulation. And depending on this phase shift related to the variable phase signal, the overall bearing related to this VOR station can be easily obtained. Now let's understand the different aspects of this VOR navigation. Now when an aircraft is flying within a range of 200 miles close to a particular VOR station, the aircraft will receive two types of signals. One is called the reference signal, and the other is called the variable signal. Now both these signals are at a particular phase difference, and the phase difference which is coded for different particular radial directions determines the bearing of the VOR station with respect to the aircraft. Let's understand this with a sequence of example. For instance, in this particular figure, the reference signal and the variable signal are at a 0-degree phase, and hence the plane lies at a 0-degree radial with respect to the VOR station. In this case, the two signals are at a phase difference of 180-degree, and hence the plane or the aircraft lies at a radial of 180-degree. And similarly, similar analogy works for the 90-degree and the 270-degree radial directions, and for other radial courses that the pilot wishes to follow. Now let's understand this. Understand what is the equipment that is utilized by the aircraft on the by the pilot on the aircraft. This equipment is particularly called the course direction indicator. Now, there are many parts related to a CDI, and the two most relevant aspects that the viewer need to understand is called the OBS. Now this OBS is a short form for Omni Bearing Selector. So as I mentioned to you earlier, the pilot can, based on what the pilot has planned according to the flight plan, the pilot can actually select what radial course the pilot wants to follow towards the VOR station, and based on this another aspect related to viewer CDI is the to from indicator. Now a to indication is basically represented by an up arrow, whereas a down arrow represents the from direction. So when I'm talking about the to and from indicators, it basically means that will tell the pilot whether the plane is approaching towards the viewer station corresponding to, and whether the plane is approaching away from the viewer station, that is corresponding to the from indication. Now, as I mentioned to you, this indicator indicates whether the aircraft is approaching towards the station or going away through the usage of this particular indicator. Let's understand what are the different deflections that are associated with a VOR CDI equipment. For instance, a plane has selected a course of a particular course and is on the selected path. The CDI indicator will be aligned in the middle and also will be showing a to direction if it is approaching from the to sector. If the plane is, because of the presence of wind, if the plane has now deviated 6 degrees to the right, the needle will point to the left. That is, the needle will tell the aircraft to turn towards the left so that he can intercept the pre-selected course leg. And in this case, the CDI will tell the aircraft to turn 6 degrees towards the left to intercept the pre-selected course. Now, despite the usage, despite the enhanced usage of these VORs, there are many drawbacks or anomalies related to VOR operation. First and foremost anomaly is called the cone of confusion. So, as we approach a VOR station, the CDI needle gets very sensitive. It approaches from to and from in a very rapid manner, and hence this creates a sense of confusion. In fact, when the aircraft is immediately above the VOR station, the to from indicator turn to off, and hence will in the off position. So whenever the pilot determines that the off position has been obtained, he or she will understand that the aircraft was flying immediately above the VOR station. So after the passage of this particular cone of confusion, the CDI indicator or the to from indicator will switch on to the from indication. The other drawbacks associated with VOR station is that the VORs are they do not lack they lack heading sense. So VORs do not VOR operation is irrespective of what heading the aircraft is actually flying. For example, in this particular case, in this particular case, the aircraft is operating in towards the right of the radio navigation is. As the time passes, the plane has intercepted the pre-selected course and is showing a 0 degree deviation, but still it is not it does not understand what the overall heading is, and hence it can create a sort of confusion within the pilot as to what heading the pilot is supposed to follow. So this type of anomaly is also very crucial for aviators to take note of while making use of VOR equipments. The third anomaly related to VOR station is called the reverse sensing. For example, this particular anomaly arises when the pilot has reciprocated the course than what reciprocated his course on the dial. For example, he wanted to carry he wanted to follow a 250 degree path, but he has by mistake set up a course of 70 degree. The needle will be centered on the proper course. However, the indicator deviation from the center so basically when the plane is on the true course, the CDI will show a particular intersection with the leg. However, in such a case, when there is reciprocity of the overall calibration, the indicator will show the deviation in an opposite manner. So if we are actually deviated to the right, the needle will also deviate to the right instead of being on to the left. So the CDI will be actually showing the pilot to deflect in a direction opposite to what is actually required. This phenomena is called as reverse sensing. In order to mitigate this type of anomaly, pilots make use of an advanced version of VOR, the VOR CDI, which is called the horizontal situation indicator. Now this is a combination of this is an advanced version of CDI, and because of the underlying methodology that is used in this is free from reverse sensing anomaly that was previously discussed with you. One of the most important navigation aid that is used by pilots across the globe to carry out navigation is called the distance measuring equipment. Now this equipment is basically used to estimate the slant distance between the aircraft and the beacon. This particular navigation involves two systems, one the DME ground station and the aircraft. The aircraft will send a DME interrogation signal to the ground station. Based on the receipt of this signal, the ground station will send a response signal which is called the DME reply signal, and the equipment on board the flight will calculate the difference of time difference between the transmission and receipt of DME response signal, and based on this time difference, the DME will be able to calculate what is the slant distance or the distance between the plane and the beacon. Now, as you can see, this distance is not actually the ground distance. In order to calculate the ground distance, the DME equipment can make use of altitude data that is available through the usage of altimeter, and henceforth calculate the ground distance. Now these operate in a ultra high frequency range and hence are limited to line of sight communication. So when we are talking of line of sight communication, we mean to say that the aircraft should be in the view of the transmitting ground station, and if there is a hindrance between the aircraft and the ground station in the form of any obstruction like a mountain or any building, the signal accuracy will be hampered. This is called the line of sight communication, and ultra high frequency range operates with this particular constraint. Apart from DME, there are many other navigation tools that are used to carry out navigation. First and foremost is called the inertial navigation systems. Now these type of navigation systems came into picture when there was a requirement to carry out navigation on a transatlantic flight. So for example, whatever radio navigation systems we discussed previously, those are limited by their range, and most of them cannot actually be used to carry out precise navigation in the sparsely populated areas like deserts or oceanic regions. So in order to carry out navigation in these type of regions, inertial navigation systems are comprehensively used. So these inertial navigation systems make use of a inertial management unit on the aircraft. As I mentioned, these operate based on the principle of gyroscope. Now this principle of gyroscope was mentioned to you in the previous lecture. I'll just brief you again. So these gyroscopes basically make use of a number of gimbals and a spinning gyro. The spinning gyro, when it is rotated in a particular axis, it retains its axis of rotation, whereas the outer gimbal, they are free to rotate in any orientation. Based on the rigidity of the spinning axis, the overall deviation from a particular axis, that is longitudinal, lateral or a direction can be obtained, and through a series of calculation that is carried out by the INS system or the IMU unit unit on the aircraft, the overall velocity, altitude, horizontal position, and the and other navigation parameters can be established. Now these INS systems basically make use of two subsystems, that is gyros and accelerometers, and through a series of calculations the different navigation parameters are calculated. The other navigation tool that is used for such flights is called the global positioning system. Now these operate based on the fact that the aircraft will receive signals from more than 3 satellites, and based on a triangulation of these 3 signals, the overall coordinate of the aircraft can be obtained. It is the combination of this GPS or the global positioning system with the equipments available on the aircraft that the aircraft is able to operate in a very efficient manner and in a very precise manner. Apart from apart from considering what are the available routes to the available navigation aids along a particular air navigation along a flight plan, air navigation the air navigation process further includes consideration related to various airway altitudes. Now these airway altitudes are further subcategorized into 3 categories. One is called the minimum en route altitude. Now minimum en route altitude basically corresponds to that minimum altitude in which the aircraft can operate depending on the reception of the signal. So these are basically determined by which is the minimum altitude at which efficient navigation system in which efficient signal reception can be obtained, while also complying with the minimum obstacle that is available en route. Minimum obstacle clearance altitude corresponds to what is the available minimum altitude for the aircraft to operate in the plant course, whereas the third one, that is maximum authorized altitude, this also corresponds to the altitude which will be useful to receive accurate signal reception and a signal which is interference free and also complies with the obstacles en route. Now apart from en route altitude consideration, there is navigation associated with landing phase or the approach phase also plays a very critical role in the air navigation process. In fact, I state as a pilot, I understand, as a ex-pilot, I understand what is the relevance of a landing. A flight that lands well ends well. So the approach leg or the landing phase is one of the most critical parts of air navigation, and this small phase of aircraft flight is considered very comprehensively while carrying out the planning. So this is basically called the overall navigation residing within this phase is called the terminal navigation. How this works, the pilot firstly switches on to the terminal control frequency. So all controlled airspaces are allocated certain frequencies for different parts of the airspace. So for the terminal phase, there is a particular terminal control frequency. The pilot will tune on to this frequency and subsequently request clearance to land. Based on the outside weather conditions and the applicable rules, the ATC controller will provide the required landing pattern that needs to be followed, and subsequently after obtaining the landing pattern instructions, the pilot will make use of the navigation tools that are available at his disposal. Some of these include the visual aids as well as the instrumental tools. As far as the instrument tools are concerned, the two most important equipments that are used to carry out this phase is called the glide slope and the DME. In fact, this type of system is called the systems that make use of landing, and the landing that makes use of instruments to carry out the landing is called the ILS system. These ILS systems basically make use of many equipments like localizer, glide path, marker beacons, and DME to guide safe landing of the planes. The localizer basically determines what is the provides horizontal guidance to the aircraft with respect to the approach leg, whereas the glide slope will provide vertical guidance to the aircraft. Details related to this particular system will be elaborated in the slide in the presentation given by Professor Pant in a in one of the later lectures. DME, as I mentioned to you, is the equipment that is used to measure the distance from the threshold, and the marker beacons are basically visual markers that are provided to the aircraft to give visual indication as to what is the overall location of the aircraft with respect to the approach leg and with respect to the distance from the threshold. So, in conclusion, we can say that navigation through radio communication plays a very crucial role for aerial navigation. Apart from the instruments that are available with the pilots on board, navigation carried out through radio communication is a very crucial part. The earliest radio navigation system that was used to carry out air navigation was called the force course radio range. Subsequently, the aviation industry ventured on to other instruments to carry out air navigation, which was initiated by the usage of NDBs and VORs, and this presentation has provided you details related to the usage of these two basic radio navigation equipments. VORs are one of the most comprehensively used navigation aid to carry out air navigation, whereas DME and ILS systems are a key part to carry out safe operations during the approach phase. So, with this, we end our lecture on the topic of air navigation. In the next lecture, we will be covering subjects related to the third critical pillar of efficient air traffic management, that is surveillance, and we will also try to understand what are the different onboard avionics that are used by aircrafts to carry out efficient CNS operations, that is communication, navigation, and surveillance. See you then. Bye bye.